Hi everyone, and welcome to the webinar. The subject of today's presentation is Advanced Setup for Challenged GNSS Urban Environments, and the presenter is my colleague Sam Soliman. The presentation will last approximately 30 minutes, and there will be 15 minutes at the end for questions. If you have a question, you can submit it at any time during the webinar using the GoToWebinar window, and we'll go through as many questions as we can at the end. The webinar is being recorded, and a recording will be made available to everyone who attends. So thank you, and over to you, Sam.
Thanks, Kit, and welcome everyone, and thank you for joining the webinar. So before we start, I'm just going to mention that I'm assuming some familiarity on your side with NAVconfig and with the basics concepts of the setup and warm up. We will go through all of this. So if you have any questions, by all means, as Kit said, do commit them and we will answer them at the end. So the focus of this webinar will be data collection, specifically with land vehicles in a challenge GNSS environment, such as urban environments. We'll quickly look at the role of the INS. What do you expect from the INS in a similar context? The issues that can prevent you from getting an optimal output from the INS, and what to do. The best part of the webinar will obviously be on the advanced settings, what to do in order to get the optimal INS output. So a quick word on what challenge GNSS mean. If you are here, then I bet you have a pretty good idea of what a bad GNSS could be. Just to have some common ground, so we are all on the same page. Challenge GNSS means a signal that is dealing with a lot of obstructions and deflections. So obstructions means that the GNSS signal will not reach the receiver in the first place. Deflections means that the receiver will get GNSS data, but only after it has been deflected several times from a number of obstacles, such as buildings. So the data will be basically wrong. The trace that you see here is the GNSS only trace logged in a pretty urban environment. This is New York City. So the role of the INS. The INS obviously is responsible for providing navigation data that will be required to correctly locate the vehicle and all the sensors that you will have on it in the 3D space. So time, first of all, so we can synchronize everything to the same GPS time. Position, either in global coordinates, lat, lon, alt, or if you have a local coordinate system set, X, Y, Z. Velocity on all axes and orientation angles, heading pitch rule of the land vehicle. Obviously, it goes without saying that having all of this measured accurately throughout the data collection is critical. So the INS needs also to guarantee integrity and solidity of the data. Issues that can prevent you from getting optimal output. As you can see in this list, I did not include the environment. Arguably, in this context, the environment will be the main obstacle probably. But the reason it's not in this list is that we cannot change it. It is what it is, and we only have to cope with it as best as we can. And in order to do that, there are a number of steps that we can complete. So the things that can get you, prevent you from getting that optimal output is one of these: either not having an ideal setup of the system, a less than ideal configuration, a wrong initialization, or an incorrect warm-up of the INS. So we will go through all of this, the way to get them right, have them correct, and also at the very end, I'm going to add some information that you will hopefully find useful. So we start with the setup, the physical setup. First of all, you need to have your antennas properly mounted with suitable ground plane, so protections from multipath. Try to always have the antennas above everything else that you might have on the vehicle, so that nothing can get in the way of the GNSS signal. Antenna separation is important mainly for heading accuracy. which is the whole reason to have, a dual antenna system rather than a single antenna system. So at least 1 meter separation. If you can manage to have 1.5 meters or 2 meters on a land vehicle, then even better. It will help your heading accuracy. Mind EMI, because you are likely to have a number of devices on your vehicle, whether that because of mobile mapping applications or autonomous vehicles applications, you are likely to have a lot of devices. A lot of these will be likely source of EMI. So as a rule of thumb, we say keep any device at least 1 meter away from the GNSS antenna. You might get away with a shorter distance depending on how strong a source of EMI that device is. So 1 meter is a rule of thumb. You should be safe with 1 meter. Mind cables, if they are not properly insulated, they can be a source of EMI. So route them away from the GNSS antenna. Use higher grade units. OxTS does provide a range of units. They are meant for different purposes. If you are in a challenging GNSS environment, it means first that you want the best GNSS receivers that you can have in order to get any GNSS data you can get. And because you will be relying less on GNSS data, since it won't be ideal, you will be relying more on the IMU data. So you want the IMU also to be the best possible. So our higher grade units are basically RT3000s and Survey Plus. Use higher grade antenna, better at reception, and often they will have embedded protection from multipath. If possible, use aiding devices such as wheel speed sensor. More on this in a bit. And a very important aspect is to enable the tracking of multiple satellite constellations. So you can have as many satellites as you can. In a challenged environment, you are likely to have few satellites because a lot of them will be obstructed. So if you have more satellites, more constellations enabled, such as GLONASS, Beidou, you have a better chance of having, more satellites that will help you out. The following is an example of what difference it can make to have more satellites available. So that is the same data set processed first in the same way that it was collected, so with GPS and GLONASS both enabled on the system, and then reprocessed by disabling GLONASS and leaving GPS only. So in the first case, the red line, the solid red line, that's the position mode, that's integer, solid integer throughout. And the dotted red line corresponds to the position accuracy, so that's about 1 centimeter. In GPS only, you can see that position mode was at 22, that's differential mode. And accordingly, position accuracy was around 30-35 centimeters. And only at the very end, the system managed to go back to integer, and hence the position accuracy dropped to 2 centimeters. Situation on the ground, so the red line, you can see it, it's solid, smooth, while the blue one is more uncertain, flipping sides relative to the red line, and that is because it had 2 or 3 fewer satellites, which were basically GLONASS satellites that it didn't have available. Correct configuration. There are a number of things that you can do to set your system, in the ideal conditions to deal with a challenged GNSS environment. So first of all, configuring the system basically means measuring the lever arms between IMU and primary antenna and the orientation of the INS in the vehicle accurately. And then in this specific context, an important thing would be to tighten the tolerances on those measurements. The reason why tightening the tolerances is important is that you are reducing the uncertainty that the system will have to cope with by doing that. But obviously, before you tighten the tolerance, you need to be sure of what you are doing. So ideally, you would leave the default tolerance to start with, that's 10 centimeters on lever arms and 5 degrees on orientation, and complete a thorough warm-up. We'll see in a minute what that means. Call it a calibration run. So you can get all the settings right. You will leave the system to figure out what the exact settings are. And then through the improved configuration tool, you will apply this improved configuration to the system. So you are guaranteed that your measurements are taken absolutely accurately. The calibration run needs to be completed in RTK or PPK position mode. So either you have corrections in real time, or you can process the warm-up calibration run data with RINEX files with differential corrections in post-processing and get the improved configuration from the processed file. Especially if you are using the same configuration time and again, I really recommend you do this. You run a calibration run and then use the improved configuration tool, because in this way, this improved config will be saved on the system and you can use it time and again. You only need to bother once, to complete this proper warm-up. Alternatively to doing this, if you are confident about the accuracy of your measurements, because for example, you are based on a CAD model, you have built a mounting for everything, so you know exactly what all the distances are and all the orientation angles, so you can tighten your tolerances manually to 1 or 2 centimeters to 1 or 2 degrees. Keep always in mind that setting a tight tolerance on a wrong measurement will be worse than leaving a tolerance loose. So only tighten the tolerance when you are sure of that. There is one measure that the system will not refine, and that is the 3D distance between primary and secondary antenna. This will be always up to you. You have to measure this accurately and set the tolerance to 1 or 2 centimeters. The system will refine the height offset between antennas and the orientation between the two antennas, but not the distance. So the improved configuration tool, you can find that in the home page of NAVconfig. You click on that button and it takes you from there. This is an example of improved configuration. You can see how the system improved the value of the orientation angles and tightened the accuracies from 5 degrees down to 0.02. Also, you can see how the lever arms have been corrected. This was a good configuration to start with. As you can see, all the original settings were within 10 centimeters, which is the default tolerance from the actual landing point, if you wish. But the system managed to improve that and then tighten the tolerance to 1 centimeter. Same for secondary antenna orientation and height offset. You can see how tight the tolerances are. Alternatively, as mentioned, you can do that manually, tightening the accuracies manually, and you can do that in the advanced tools accuracy section of NAVconfig. So other settings, GNSS related settings. First of all, the GNSS control. So I would recommend that you use GXIX mode. That's the tight coupling mode of OxTS. That is recommended over receivers mode because it performs better in urban environment. One of the reasons why is that if you have fewer than 4 satellites, the receiver will not be able to lock on a position mode. So basically, you are completely relying on the IMU in that case. But if you are using GXIX, then specifically the IX bit of it will use the data from 2 or 3 satellites, not to have a complete position fix, which is not possible without 4 satellites at least, but it will use that data from single satellites as an aiding to the IMU. So you still use that data. And another advantage is that because you have a partial solution, say, based on 2 or 3 satellites, as soon as you get the 4th one, the system will be much quicker to relock on a proper position fix. So it gives you shorter time in no position mode by using GXIX. GXIX is compatible with GPS satellites through all modes up to GX integer. It is compatible with GLONASS up to GX diff with all kind of base stations. It is partially compatible with GLONASS at GX RTK or GX integer level. Partially compatible means that you have to have a compatibility between the GNSS receiver on the unit and the GNSS receiver on the base station that is providing these corrections. If you want some peace of mind, it might be helpful to use mixed mode. So you leave it to the system basically to choose whether you want receiver mode or GXIX mode at any given time. If you have an older firmware that doesn't support mixed mode, then I would recommend you use definitely GXIX mode. Even if you are not in all the time in in urban environment, but you are in a mixed environment, still use GXIX mode. This is how we enable it in the Advanced Tools GNSS Control section. And this is a comparison between the same data set processed in GXIX and receivers mode. The red line, GXIX, is solid, as you can see, despite the fact being an urban canyon or covered by trees, whilst the blue line, the receivers mode, it didn't have any position mode because it had fewer than 4 satellites at that point. So it drifted, as you can see, to the left. Whilst, as I said, the single satellites data was used as an aiding to the IMU, even whilst in between buildings. Other settings, GNSS weighting, that's basically how much you can trust the GNSS data. I would recommend some obstructions. You can use frequent obstructions, but that would limit the trust in the GNSS data heavily. So do not start with that. You can always try to post-process the data, changing this specific settings and see the effect of that. But the best starting point is some obstructions. GNSS recovery, that's basically it determines in case of disagreement between the IMU and the GNSS, and you will have that in urban environment, how much to trust one over the other, and how quick the system should trust the GNSS over the IMU. So how much basically the GNSS needs to keep repeating the same thing for the system to believe it. So in this sort of environment, you shift this trust so that the system will have, will be less quick to believe the GNSS. It will take the GNSS longer to be taken seriously, put it this way. So the system will prefer the IMU over the GNSS, and it will take many more GNSS updates, position or velocity updates, before the GNSS is taken again for real, for correct. The best way to do this is to run a few attempts in post-processing to fine-tune it, the exact number of updates that will be needed before the system believes the GNSS again. Because there is no one size fits all in this case. It would pretty much depend on the specific situation. So if you want to use it, I would recommend you fine-tune it in post-processing. This is where you set the weighting of the GNSS, so that's in the environment section, and as you can see, I've selected some obstructions. And this is GNSS recovery in the advanced tools section. So the default that we have on our system is 20. That's 20 updates, that will be rejected before the system believes the GNSS. The more heavily urban environment you have, the more I would increase this number to 100, for example. Do not use never believe unexpected measurement, because that would be too much. But you can definitely, in post-processing, as I said, try playing with that value and see which one is the best. Other settings, advanced slip. So this setting is very important. It's freely available on our systems. It will enable the system to do two things. One, to calculate any orientation misalignment between the unit and the vehicle, which is critical, obviously, because any data that you have, that's the data of the RT. And so the motion of the RT, but obviously what you are interested in is the motion of the vehicle. So you need to make sure that there is no misalignment between RT and vehicle. The other thing that it does is it helps limiting the heading angle drift when you have a GNSS outage, which can happen obviously in urban environment. And by reducing the heading drift, it will reduce the position drift. So it will help your position accuracy. This is where you enable the advanced slip, lateral and vertical. Lateral is more important, but do enable both. That's in the hardware setup section in NAVconfig. V-speed sensor, it provides an additional source for velocity data, obviously. So it helps in measuring velocity, especially in GNSS outage, and especially at very low speed or absence of motion, which again can happen in urban environment. Think of traffic lights, for example. By measuring velocity more accurately, it means you can measure distance more accurately, which in turn means that you can measure position more accurately. With the newest V3 models that we've released, you can have not just a V-speed encoder used as, say, an aiding to the IMU, but you can have what we call generic aiding. So any other device, for example, an external IMU, a LiDAR, anything else that you can use as a external generic aiding to the IMU solution can be implemented with our systems with V3 models. This is where you enable the V-speed sensor that's in the advanced tools section of NAVconfig. And to give you an idea, this is from a test that we've run. Basically, we've collected data in open sky environment, and then we blanked the GNSS data for 10 seconds, 1 minute, 4 minutes, so on. And we had the V-speed sensor and the advanced slip turn on and off in all the possible combinations, as you can see, so that we can tell the effect of having the V-speed sensor and the advanced slip settings enabled in GNSS outage. So at 10 seconds, there is no big difference, but at 1 minute, you can already see a significant difference between having them both enabled, 30 centimeters drift after a minute of complete GNSS outage, and about 1.70 meters when you have neither. After 4 minutes of complete GNSS outage, if you have them both, then the drift is just 2 meters. If you do not have any aiding whatsoever, then the drift can be above 100 meters. Even by just having advanced slip enabled, so no external equipment, just something that is already available on our system, you can limit the drift after 4 minutes of complete GNSS outage to about 6.5 meters. Obviously, this is a use case. It will pretty much depend on what kind of motion you have during the GNSS outage, because this will be, can give very different results depending on what kind of motions you have. But the magnitude, the order of drift that you can expect is, showed in this table. Okay, initialization. So initialization of the system is basically about getting directions. You can initialize in 2 ways with our systems, dynamically or statically. And it is really easy to do that. What you need to do if you initialize dynamically is just to drive forward and in a straight line. So what basically you need to pay attention to is just ensuring that you have enough space to accelerate beyond the speed threshold that you set. As soon as you cross that speed, accelerating over it, the system will initialize. I recommend you set this threshold high enough, at least 5 meters per second. 10 is better for 2 good reasons. One, you avoid initializing inadvertently, while you are maneuvering to position the vehicle to start the initialization. You still need to move it, and if the threshold is very low, you might cross it before you intend to do that. And the other reason is that the faster you are traveling, the more likely you are of traveling straight, of being actually traveling straight. So set it high enough. If you have room enough to accelerate to 10 meters per second, then do it. That's the best. Whenever possible, choose a level spot. If it is not level, then it's not a problem. If you have a slope, just configure the system to not level, so the system knows you are not on a level. Static initialization, that is also possible, but remember that you need good GNSS environment if you do that, because you are static, so there is no motion, the IMU is silent, you are completely relying on GNSS, it needs to be good. Again, if you can do it on a level, if not, just configure the system to tell it that it is not on a level. If you have the correct setup, so basically a suitable distance between antennas, measure that correctly, and a suitable environment, meaning good GNSS, then static initialization can be very quick, under a minute. It shouldn't take longer than that. This is an effect of a wrong initialization. What I've done here is basically I've tweaked the configuration to have it wrong on purpose, so that the system would initialize wrongly and it will get its directions wrong. As you can see, this will affect the position accuracy. You can see that the red line, which is the original trace, is very neat and clean on the road. The blue one is off mark because the system initialized wrongly. The warm-up. So the first thing to say is that you have a warm-up window of 15 minutes from the moment initialization occurs. This is not when you switch on the system, this is when you initialize. You've got 15 minutes to complete your warm-up. Higher grade units, such as RT3000, because they are, they have stronger IMUs, they need some more time to learn about the surrounding environment. So you can use up to the entire window, I would say at least 10 minutes, if you are starting from a loose configuration. Earlier we discussed the calibration run and applying the improved configuration. So if you are starting from an improved one, then the warm-up will be significantly shorter. About 5 minutes should be enough. If you are starting from a loose config, then take 10 minutes. If you are doing the calibration run, so the one upon which you will base all of your settings, then take your time, and I would recommend you take the entire 15 minutes. If you are processing in combined mode, more on this in a bit, then the warm-up can be even shorter because the two traces forwards and backwards will help each other in improving, the accuracy. So for a warm-up, good GNSS conditions are important. Open sky spot. Later on, once you have done the warm-up, once you have your improved configuration, you can go in any urban environment that you want. But the warm-up itself, try always to do it in an open sky environment. And to have varied motion. We'll see in a minute what that means. Again, if you start from a tight config, improved configuration, that's 5 minutes. From a loose one, about 10 minutes. If you are doing the calibration run, as I said, you only need to bother to do this once, then take the entire 15 minutes. Take your time, do it properly. You save the configuration on the unit, and you need not thinking about it again. You can monitor how the warm-up is progressing in real time using NAVDisplay. That's our software. So you just need to connect basically to the system. We have a warm-up template. We have a number of measurements that you can check in real time to see how the warm-up is progressing in real time. Motion types. So the first items here are what you should always do with any warm-up, really. The key concept is to excite all 6 sensors. So, all kind of motions are fed to the system. So straight lines, high and low speed, that helps heading accuracy. Accelerations and decelerations, this for pitch accuracy. Circles, clockwise and anti-clockwise, for roll accuracy. Figures of 8, that will keep everything together and it will help horizontal position accuracy. If the ground around you does allow for that, then you can do some variations of altitude. If you have some slopes around, that's for vertical position accuracy. This is not as important as the above. Specifically for urban environment, include some short sections at very low speed or no motion, because you will have that in urban environment in the traffic jam. You will be traveling slow, you will standing still for a while. So include that in the warm-up. And any kind of motion that you can think of that will be part of your survey or data collection, include it in the warm-up. So the system is prepared. Finally, some hopefully useful information very quickly. A word on datums. You have a number of datums available with our system that you can output your position coordinates in. For North America, for example, you have NAD83. You can use WGS84. You can use ITRF to 2014, ETRS89. If you wanted a specific datum for your output, you can select that. In addition, for altitude reference, we have both ellipsoidal and geoidal. They are obviously both mathematical models. The geoidal specifically comes with the receiver. So the specific difference in altitude between geoidal and ellipsoidal, which is called undulation, is set by the receiver. If you have a better knowledge of the altitude in a specific area, altitude above sea level, you can set this undulation value. Instead of using the receiver's one, you can customize it. Do this assuming that the area that you survey or that you collect your data in is not very large, because if it becomes too large, then having a fixed undulation, which basically means a fixed altitude, will not be a fair approximation anymore. This is where you do it in the Advanced Tools Global Coordinate System section. As you see, you can select geoid as a receiver default or ellipsoid, or customize the value of the undulation. Output displacement, this is a feature that can be useful at times. Basically, you have a choice of having all the output measurements. Instead of having those at the INS location, you can have them at any point you choose. So for example, the location of one of the sensors that you have on the vehicle. You don't have to do that, but at times it can come handy. And also you can post-process the data. If you want to displace to several points, you can what you need to do is just post-processing the data and changing the displacement output position, so you have your data displaced to several points if you needed to have that. This is where you do it. Advanced Tools, Displaced Output. You only need to set basically the lever arms between the IMU and the displaced output point. Differential corrections. There are a number of them. These obviously are used to improve the position accuracy of your system. So SBAS, to start with, that is free. It's provided through satellites. Keep in mind that it is only compatible with GPS satellites. So if you have other constellations enabled, like GLONASS or Beidou, in the near future we will have Galileo, SBAS is not compatible with these. It means the system will still be tracking those constellations, but it will not be using them in real time. So if you already have few satellites, it might not be a good idea, to cut that numbers even more by enabling SBAS. The good news is that if you have SBAS enabled in real time, you can disable SBAS in post-processing and have your GLONASS or Beidou satellites back. So it might be worth trying to have it and see if the result is better. SBAS gives you a position accuracy of around 40-50 centimeters. NTRIP corrections, these kind of corrections can give you RTK or GX integer level. You will need obviously a good mobile internet connection, and if you lose connection to the NTRIP server, obviously you will lose your corrections. So many times it can be enough to apply differential corrections in post-processing only. So you collect your data with no corrections, and then you improve the accuracy later through RINEX files. The advantage of this is that you will not have any interruptions in the flow of corrections. The disadvantage obviously is that it is not in real time. So if you are monitoring things in real time, you will have to wait until you post-process to be sure that your data is as accurate as you want it to be. One important aspect is that the datum in which differential corrections are provided has to be specified correctly to the system. This information will be available from the provider of corrections, be it RINEX or NTRIP. They will tell you what datum they are based on, and you will have to tell the system about it. So if you are doing that in real time, this is the page. You can select the corrections format, enable NTRIP if you wanted, enable SBAS if you wanted, and specify the datum of real-time corrections. For post-processing RINEX corrections, you can do that through an advanced command that we can tell you about. And finally, a word on post-processing. It's worth keeping in mind that there is a number of things that you can do in post-processing. First of all, you can add differential corrections, as we just discussed, to improve the accuracy. You can process in combined mode, and I'll show you an example in a second. And in case your results were not as good as you want them, hopefully if you do all the things that I've just described, you will have good data. But still, if it happens that you don't have fantastic data, there are a number of things that you can do in post-processing by changing the configuration, by tweaking a few aspects, enabling or disabling a few things to try to it will review your data and improve it. The only thing that you cannot change in post-processing is the raw data. So whatever GNSS data you had, that's it. You cannot, simulate an additional satellite. Whatever IMU inertial data you had, again, that's it. But you can change the way the system interprets and uses this data by tweaking the configuration. Combined processing, it puts together the best outcome of forwards and backwards traces. So it has an overall result that will be better than each of the two traces separately taken. It will help your position and orientation, attitude, position accuracy. If you have in mind to use the combined mode, keep in mind that the backwards trace will have to initialize and warm up as well, the same as the forwards. So basically, it means that you will have to include a short warm up right after as well as right before your data collection, and you will have to finish your data collection with a straight line, which will be the first thing that the backwards trace see and uses for its initialization. Either that, or you stand still for a couple of minutes in an open sky spot so the backwards trace can initialize statically. So keep this in mind. You need the warm up and initialization in reversed order at the end if you want to process combined. It will still process combined regardless, but if you want the best results, then I would definitely recommend you do this. The warm up time will be shorter, so you only need to do a couple of minutes at the end, not the entire thing. This is where you select the processing mode in NavSolve. You can select simulated, combined, or both. And this is an example. The dark green line is the number of satellites that were available. So that's between 3 and 6 satellites. So, very difficult GNSS situation. The simulated processing is the blue line. This is without any corrections, and you can see that the accuracy was about 4 meters, and then it comes down slowly to about 1 meter at the end. While the red line, that's the combined processing, is 1 meter position accuracy throughout, more solid. This is the situation on the ground. Again, this is New York City. The direction of travel is from top right to bottom left. The red line, as you can see, it is solid, smooth, and in the right place, while the blue one goes over the pavement and then flip side relative to the red line, so it's more uncertain. So that's an example of difference between combined and simulated processing. Thank you.
Thank you, Sam. If anybody has any questions about any of the content that was covered in this webinar, then feel free to submit them now. Otherwise, we'll go through the ones which we have had in. So first question, if you have a setup where the RT and antennas are mechanically linked, is it better to lower the tolerance during initial setup or to leave it loose?
So mechanically linked, meaning if you move one of them, you will move the rest of the lot, I imagine that means. So if we are talking about the initial setup, as in the calibration run, then I would leave the tolerances loose and leave the system to calculate the exact measurement, the exact distances. Okay. Once that is done, keep the tight tolerances. So if you are doing the short warm up that you would do before you go into the actual data collection, then keep those tolerances tight. Okay.
Okay. That's the only question we've had in during the webinar. Giving people a bit of time to submit any questions they do have. We'll just quickly let you know this is just one of a series of webinars that we are producing at OxTS. The next series of May starts next week, and you can register to these at the oxts.com/resources hub. We also have a lot of articles written by members of the OxTS team that can be found at support.oxts.com. So these articles can be troubleshooting guides or information about features or configuration. So it's really worth looking through the articles that are available there. Okay, so we've had a couple of questions in. First, how do you provide external aiding to the latest RT other than using the wheel speed encoder?
So basically, first of all, you will have to have the feature codes enabled, the generic aiding feature codes, depending on exactly what sort of aiding is that. So is that position, is that velocity, such as wheel speed encoder, is that orientation, depending on the device that you are using and what sort of aiding it is providing, to improve what specific measurement, it will have the related feature codes that will have to be enabled on the system. And after that, what you have to do is just connect the two devices and feed the output of this aiding device into the RT. And this input will be handled by the input-output interface on the RT. Okay.
Thank you. So next question. Can data be reprocessed to correct for if you have used an incorrect datum during the initial run?
Yes, you can do this in post-processing by using GXIX processing mode, though. So you can do that basically in post-processing. The short answer is you just need to to specify the correct datum.
Okay, so next question. If we want to have a better improved settings, do we need to post-process the calibration run with data with post-processing software? For example, would using combined processing lead to a better improved settings than doing it in real time?
So two things. If you run the warm-up in real time and you have corrections, then obviously the system will provide you with a improved configuration. Now, if now you start another warm-up starting from that one, or if you reprocess the data starting from that one, then the improvement should be very, very marginal because the system has already refined those measurements. So what you could do is do the warm-up live once and perhaps reprocess the data a few times by changing slightly the starting points, but the improvement that you will get will be marginal. Marginal means, in terms of distance below 1 centimeter and in terms of orientation below 1 degree. So it depends how much what level of accuracy you are after. But if you post-process and extract the data from the processed NCOM, do not use combined processing. Okay, do not get the improved configuration from a combined processed NCOM file. Always use simulated, because combined in this specific case is not recommendable. Okay, you just use the simulated processing.
Okay, next question. What types of external sensors do you currently support for external aiding besides the device that provides velocity?
Well, for example, we've done some tests with external IMUs. So if you have another IMU that can provide, an additional source of information to the internal IMU, that could be done. We also tried to use a LiDAR that would measure the distance to, known obstacles and feed then a position aiding, in this case, based on the distance from the LiDAR to these objects to the system. It can be position, it can be velocity, it can be IMU. So basically acceleration and angular rates. It can be something that helps with the orientation, such, for example, a magnetometer that will help in giving directions. It can be a number of devices.
Okay, just a couple more questions now. If the system uses both SBAS and EGNOS, then only GPS and Galileo satellites will be used in the solution. And there's a follow-up question, which is EGNOS supported in North America?
Okay, so here is the thing. So SBAS is basically a term, an acronym, if you wish, that includes all augmentation constellations. So in North America, that would be WAS, WAAS, and in Europe, it will be EGNOS. So the difference is basically the area, the geographical area that is covered by a specific SBAS constellation. SBAS is the term that defines all of them. So by using EGNOS or WAS, you are using SBAS, if that makes sense. And depending on the area you are in, you will be using a specific one SBAS constellation. You can't use two of them. So EGNOS, for example, cannot be used in North America. It doesn't cover North America. It is meant for Europe mainly, really, and say areas close to that. So North Africa or the Middle East might get some EGNOS corrections, but definitely not North America. Okay. As for constellation, sorry, we do not support Galileo at the minute. It will be in the future. So at the minute, SBAS is only compatible with GPS satellites. Okay.
Okay, so next question. Is GX-IX mode a robust choice to use? It seemed a couple of years ago it was just being introduced. Is it now a stable choice to use?
So it is definitely a robust one. It is in fact older than 2 years ago. Perhaps we made some more noise about it a couple of years ago because it started to finally be compatible with GLONASS, as long in addition to GPS. So as I mentioned, you can use it in GX differential mode. The system will use both GPS and GLONASS satellites. In GX integer mode, it will surely use GPS. It will use GLONASS partially. I mean, partially means sometimes it will, sometimes it won't, depending on the compatibility, as I mentioned earlier, between the receiver on the unit and the receiver of the base station providing correction. So for example, if you were using our RT base S base stations, obviously there is a complete compatibility between the base S and all of our units. So if you are using a base S with an RT, you will be able to have GLONASS satellites in GX integer mode. But yes, definitely, it is a tested technology, and especially in urban environments, its performance is better than receivers mode.
Okay, and then we'll have a final question. If running the system in a variety of environments, transitioning from rural to urban environments in a single run, should you leave the system in some obstructions? Is there a way to change subsets of the run in post-process?
You can do, I would say, two things. One, you can select mixed mode. That's available with newer firmwares. So the system will automatically choose between receivers mode and GX-IX mode. So if it had RTK integer solution available, meaning the receiver is performing fine, it will go with that. Otherwise, it will switch to GX-IX. GX-IX is as good as receivers mode in all environment. It is better in urban environment as a general rule. The other good news is whatever settings you have in real time, you can change that in post-processing. So if you wanted, to check the difference, to see for yourself, you can enable one of the three modes, receivers mode, GX-IX, mixed, in real time, and then play with that, change it in post-processing, and compare the results. Okay, so that's also is possible. Either you change it to real time by selecting mixed mode, you leave it to the system to figure out, or you change it in post-processing and you specify which one you want. Okay.
And just to finish to that question, I don't think it's possible to have parts of a process in some obstructions and part of it in no obstructions.
Oh yeah, sorry for that. Yeah, yeah, you cannot change that, but you can change it in post-processing. Again, if you wanted, I would still leave it to some obstructions though, because you will still have a good position accuracy. And so if the GNSS data can be trusted, the system will do that. If not, it will be cautious in using it. Again, this is something like it said that you can change in post-processing, modify it to open sky if you want to see the effect, and also to frequent obstructions if you really want it. A good thing is also that once you have processed the data, it will take more effort on your side, but what you can do is process the data in different ways and then export the data or chop the processed data, taking the best outcome for each section. If imagine that you have a mixed environment, some rural open sky and some urban environment, and one processing mode gave you a better result in one case and another processing mode gave you a better result in the other case. So how to keep everything together? You can chop the processed data and export just the bit that you like for each of the two, for example. Obviously it's going to be a bit more lengthy procedure, but you can do that. There are a whole variety of things that you can do in post-processing, really. Okay,
and that's all the questions we've had. Thanks everyone for attending, and I hope you've enjoyed it and learned something.
Thank you very much. Thank you all. Have a good day.